All right, hello everyone. Welcome back to my lectures. This is the third of the quarter, and today we'll continue talking about waves, and we'll discuss a new type of interference and how it actually led to a completely new theory in physics, which is quantum mechanics. So it's a bit of a strange place to introduce quantum mechanics, but as you will see, it'll connect quite a bit to what we're talking about. All right, so just to review wave interference, which was the main topic of last week, what we saw is when there's more than one source present that's producing a wave, then those two sources may interfere as long as they're in the same, more or less, location and the same time that these waves are being produced. So how do we figure out how these waves interfere and what properties that interference exhibits is what we saw. What's important is the phase difference between the two sources. And if we looked at the total phase, we remember that there are these three terms that matter. There's the time-dependent term, the spatial term, and then the phase constant term. Now this term here, that mattered when there were the two sources had different periods. So if they were producing waves of different periods, thus frequencies, then this difference here would be non-zero, and that led to phenomena of beats. What beats means basically is that the interference itself is time dependent. When there are no beats present, interference is fixed in time. What might change is how interference is as a function of space. So for example, the next term, which has to do with the path length difference. What is path length difference? It's basically the distance difference between the two sources. And interference, because it depends on that, the type of interference you experience depends on where you're observing this interference. So even though the two sources may be fixed in space, where you're standing to observe or where you're trying to measure the interference may result in different type of interference due to this term of path length difference. And here, if we're considering cases where the periods are the same, that implies wavelengths are the same because interference is happening in the same medium. So what really matters is just the difference between these x's, which is exactly the definition of path length difference. And then finally, there's this one more term that has to do with the phase constant difference, which is basically asking the question whether the two sources are synchronized or not. So if the two sources are producing crests and going, let's say, yes, if they're producing crests at the same exact time, that they're in sync, but if one is producing a crest while the other one is producing a trough, that means that they're out of sync, and the phase difference is exactly half a cycle, which we represent as pi. Of course, these are not the only two examples. You can have two sources that are, let's say, pi over 4 out of sync and so on. Now, the type of interference that we looked at is there these two extremes, constructive interference, and this is when the two waves perfectly line up so their amplitudes add perfectly, and that's satisfied when the phase difference is exactly a multiple of 2 pi. Now, destructive interference, which is the opposite of constructive, that's when the crests and troughs meet each other. So they subtract and you have no wave there, and no amplitude there. That's why it's called destructive interference. And the condition for that is it has to be an odd multiple of pi, the phase difference. Of course, these are these extreme cases. Anything in between is known as partial interference. All right, so one thing that I haven't really discussed yet is, why do we care? When do I actually see interference? And, it comes up quite a bit in different physical phenomena, but I just want to point out some interesting cases where interference has been seen. So in around 2016, I don't know if you remember, but this was sort of all over the news. There was this very huge discovery in the world of physics, and that discovery was gravitational waves. So although gravitational waves themselves were first predicted by Albert Einstein back in the 1920s, no one has been able to measure them. So, until you actually measure it, it's just a theory. But finally, in 2016, they were measured for the first time. So what exactly are gravitational waves? Well, they're waves that travel through space-time. So unlike, for example, sound waves that we've talked about, which is something that propagates through air, or water waves, these are waves that actually create ripples in space-time itself. So as these waves propagate outwards, what they do is they squeeze and stretch space itself. And what creates them, as we have seen already, to have waves, you need some kind of source. So to have gravitational waves, you need a pretty large, huge source, a source that creates a lot of energy. So an example of that is two black holes colliding. So as you can imagine, that's a huge astronomical event. So when that happens, that creates these gravitational waves, and then after that travel outward. But as we know, first of all, these events are not so common, or at least they're not happening nearby our Earth. And also, as we know, when waves propagate, the amplitude and the wave and the intensity of that wave decreases as the wave spreads out in space. So the point here is that by the time it reaches Earth, these signals are really small. So it's not that we're just sitting around and suddenly we feel space stretch and squeeze. This turns out to be a very, very tiny signal because it happened somewhere, first of all, a long time ago and very far away in space. But clever scientists came up with an experiment that actually uses this idea of wave interference to detect these gravitational waves. So let's take a look at how that's done. So this is an aerial picture of this experiment. So let's see what it does. So basically what the basic principles behind this, and this is known as the LIGO experiment, is there's a laser that gets sent out and it hits this beam splitter. And what this beam does, it just basically splits this laser into two lasers here that go perpendicular to each other. So one half of it travels this way down this path, and that path is 4 kilometers long. And the other one goes straight, also 4 kilometers. So you could see these two arms of this aerial picture of this experiment. They're about 4 kilometers each. Now there are mirrors at the end of this 4 kilometers. These light rays reflect, they meet back again, and they're detected. So the idea here, where does interference come into play? Well, the idea is if both of them travel perfectly 4 kilometers and then they combine back together and get detective, then they should interfere perfectly constructively. Their path length was the same. But if you imagine there's a gravitational wave which is coming, you can think about the wave fronts, let's say, coming this way, perpendicular to this arm, and if space is being stretched and squeezed as this gravitational wave is moving through it, then the path that this laser takes should be different than this one. And when they get recombined and get detective, then the interference will be slightly different. But so, it sounds like it's a pretty neat experiment, but what makes it really impressive is the fact that the signal that these gravitational waves create is actually really, really small. So if you look down here on my slide, it says that the the size of this signal that they detected was of the order of 10 to the minus 18 meters. So that's how much that path changed. This is a really, really small number. It's smaller than the size of an atom. So just to think about that, you know, relative to the 4 kilometers path, they're able to detect such a small signal is really, really impressive. So this is quite a sophisticated experiment. And what the first thing that it detected was this event of 2 black holes colliding, which happened 1.3 billion light years ago. So light years is actually a measure of distance. It's how much, what is the distance it takes for light to travel a year, but it also gives you some information about time. So basically what it's saying is that that event happened 1.3 billion years ago. So normally when we say, for example, a star, one of the closest stars to Earth, Alpha Centauri, when we say that's around 4.4 light years away, what we're saying is that's how far it is. So you can take that distance, how much it takes light to travel 1 year, and multiply it by 4.4, and you get that distance. But also what it tells us is when we look up at that star and we're seeing its light, what we're really seeing is how it looked like 4.4 years ago, because that's how much it took, how many years it took for that light to reach us. So anyways, this is a very cool example of using interference to detect something that's so tiny. And you know, it's this gravitational wave. So this was a huge deal, and I encourage you to kind of Google around and read more about this. One question you might think about is, well, the signal is so small, 10 to the minus 18 meters. How do they know that that's what caused it? You can imagine there could be a train passing by there, you know, even 20 kilometers away. That little vibration, even far away from that train, could cause a signal like this. You know, as you see, this experiment is in the middle of nowhere, and that's exactly the purpose, is to be away from all type of natural random noise, but still you can't avoid it completely. So the way that they sort of make it more valid or more convincing that in fact it was gravitational wave is that they have 2 of these. So in fact, they have built one of these LIGO experiments in Washington State, and another one is, I believe, in Louisiana. I'm not sure which one this picture is of. And, you know, that's many miles apart. And it turns out when this was detected, exactly the amount of time it takes light to travel later, that same exact signal was detected at the other detector. So, you know, knowing how fast light travels, gravitational waves travel at the speed of light, and the distance between the 2 experiments and the fact that, you know, they saw the same type of signal made it pretty convincing that it wasn't some outside noise like a butterfly flapping its wings or train going by, but it was indeed these gravitational waves. And now they're building several other ones around the world as well. All right, a more practical application of interference, or more everyday application, is noise canceling headphones. So you've probably heard of these, have seen them, or maybe even used them, especially on an airplane or a place like that where the outside background noise is very annoying. So how do they work? How do they create the silence? Well, what the noise canceling headphones do is that they detect this outside background noise. So that's, let's say this is a wave representing noise created by external source. Of course, it wouldn't be such a nice wave because typically external noise is a combination of many different frequencies. So it would be something much more jaggedy, but let's say if it was one frequency, then so the speakers or the headphones detect that, and then they create their own signal that they send out, which is exactly opposite. So in this drawing, it's kind of drawn the same, but the point is they create a signal which is exactly half a cycle out of phase, or exactly opposite of that, in such a way when then the two interfere, they interfere destructively, and they cancel each other out, thus creating silence. So these work really well for some kind of continuous background noise that the headphones are able to detect and create that opposite signal. If there's some sudden loud noise, like, you know, you're walking down the street and there's a horn, they're not as good as handling that. But noise on an airplane or something like this, they work pretty well for this. All right, so another type of interference that we already briefly talked about, and you worked on this in DL, comes from this Young's double slit experiment. So I'll talk a lot more about this today, and we'll see actually why this experiment is kind of really, really important in physics, although it seems a little bit abstract when you're just doing this in the lab. So just to remind you what it is, so this was generated by this PhET simulation, something that you'll play with in one of your FNTs this quarter. What is it is when you take a laser and you shine it through some kind of boundary that has two slits, as you see here, what happens is that the slits themselves act as sources. So when they act as sources, then they emanate these waves outwards, and then those two waves end up interfering. So although we start with one source, which is the laser, having these two slits, it's as if we have two sources, which then interfere with each other. So when then if we take this and we project it onto a screen, and it's not very obvious here, but you should have seen, looked at the video, which was created of something you would have done in DL, where the TA projected this onto the blackboard, and you saw in that video kind of really bright red spots. Here we're using green light. So these fringes here, you see, those represent areas of constructive interference because the two amplitudes are adding up, so you get brightness, where the dark fringes in between the dark ones in between the bright ones, they represent regions of destructive interference, where the amplitudes are canceling. Thus, you see darkness or no light. So it's kind of analogous when we talked about speakers or sound from speakers interfering. The bright fringes would be analogous to where you're hearing the sound the loudest, and the dark ones would be equivalent of where you're hearing no sound. And here, what matters, because we have the same source, so there can't be a phase difference. You will see some examples, maybe in practice problems, where you're asked to think about if there was a phase difference, what would happen here. But in the standard double slit experiment, there's no phase difference. So the only thing that causes interference is path length difference. So if we're looking at the central bright spot, what makes it central? It's the same distance from each source. So there's no path length difference. So that's why you get a bright spot. But then you can imagine going some distance like over here, where the path it takes for the ray to come from this direction versus this one is exactly one wavelength. So that means that it took the distance from this slit to that bright spot is exactly one wavelength longer than the distance from this slit to that bright spot. So again, we get constructive interference, because remember, condition for constructive interference when there's no phase difference, phase constant difference, is just a multiple of wavelength. So this is 0, this is one wavelength. This is again one wavelength, but in the negative direction, in the sense that now it's the distance from this slit to here is one wavelength longer. Now for destructive one, it's multiple of half a wavelength. So to go from here, if we're looking at this spot, it means it took light to travel half a wavelength longer to this location from this slit compared to that slit. So that's the condition. And then everything kind of in between is partial interference. So we also looked at how to kind of predict some things. So given the distance between, let's say, two bright spots, which we'll call delta y, which is in this equation here, given the wavelength of light, so here we're using green light, if we were using red light, it would be a different wavelength, so you would get different types of interference patterns. And then given the distance to the screen from the slits, you can figure out the separation between the two sources. Now, this equation you see here is only valid in this, what we call the small angle approximation that you derived in DL, and there's also a video where the TA goes through this derivation as well. So this is valid when this distance here from the slits to the screen is much, much greater than the separation here. So at least the real experiment in DL, you know, let's say this distance was on the order of a meter or two, where the separation between slits was a millimeter, or I don't exactly remember, but this was a very, very small number. You know, here with the simulation, you could see that this approximation would not be very accurate because this distance is not much longer than that distance. So you can't exactly use this equation. So what you're asked to do in the FNT is actually use this equation and then think about, you know, why you're not quite getting the right answer there. Now, n here is this integer which basically counts the bright spots. So if you increase n, you're also increasing delta y. So if n is 1, you're just talking about the distance between the central bright spot to the next one. If n is 2, so you don't see that here, it's out of the range, but let's say there would be another one up there. So you see you would be doubling delta y, and you would be doubling n, so you still get the same, you know, you're not changing the distance between the sources. This minus, that just means that, you know, when we go up, let's say we count that as positive. When we go down, we count it as negative. So if n is minus 1, then this delta y is a negative number because you're kind of measuring down. So, but it's perfectly symmetric about the center, whether you go up or down. All right, so this is kind of another summary of the double slit experiment. But let's think about, you know, why is it so important? Why do we care? And what did it mean historically? So this experiment was first conducted by Thomas Young. That's why it's called the Young's experiment in 1801. And the conclusion here is that when he shined light passing through two slits, there was this diffraction pattern. And this diffraction pattern can only be explained if light behaved like a wave. And that was important because back then there was a huge debate. It was not clear whether light was a particle or a wave. So there's this scientist, Christian Huygens, his name came up a bit already. He's the one who said that you can represent light as, or every point along your wavefront as a source of light. So he really believed that light is a wave. Where Isaac Newton, which you heard a lot about him in 7B, he was all about dropping apples and bouncing balls. So he worked more with particles, and he I guess conducted some experiments that made him think that light is a particle. So there was this debate going on, but then when Thomas Young's experiment, the double slit experiment, came out and his results, he said, well, look, I just showed you that light is indeed a wave because it behaves like a wave. You get these diffraction patterns that could only be explained by a wave. So the debate was, I suppose, settled for many years until Albert Einstein came about, and he said, well, wait a second, there's more to this story. So we'll get to that a little bit later in this lecture. But before we get to that, there's another type of interference that we need to discuss. So far when we talked about waves up to this point, we talked about waves that propagate in space continuously. So we said in the very beginning of the quarter, we said that a wave can either move right or left. When we have two such sources, they again moving right or left, but then they can meet in space and interfere and so on. What we haven't looked at yet is what happens when you confine that wave. In other words, you don't allow it to continue traveling in space forever, but there's something that stops it and also allows it to reflect. So in other words, can a wave interfere with itself? And the answer is yes. So if we look at this model of a string, which is tied to two locations. So here's a driver, that's the source of the wave. So it's just kind of moving up and down with a specific set frequency, allowing this wave to propagate. So, if there was no end here or no boundary, then this end, if the string was infinitely long, it would just continue traveling, in this case, to the right in space. But if we introduce a boundary, so we confine this wave to this space, what happens? When this energy or this wave propagation gets to this end, it will reflect, and it will reflect and go to the left. So there's still, if this driver is still oscillating with time, there will be some of its wave going to the right and some of it going to the left as it reflects back. So it's as if now we have two separate waves which interfere. So although the source is the same, there is going to be interference of the incoming or the, let's call it the outgoing, and then the reflected waves. And one interesting thing that happens is the way these waves interfere when these waves are confined is they create what is known as standing waves. So this is sort of really difficult to see unless you see it live. So if I was doing a live lecture, I would show some cool demos where you could see that, but there are a bunch of stuff on YouTube and other places. So I really encourage you to Google standing waves and look at videos to really see what it means for a wave to be standing. So what you see here is actually a bunch of pictures superimposed to each other. So it's really just one rope. And what those kind of in between lines represent is what's happening as a function of time. So what basically happens is there's still motion. It's not that the wave is stuck in place and not moving, but that motion is just up and down. So what you would see here, if this was a movie of the standing wave, is this rope oscillating, or the string oscillating up and down in these locations, these three locations, and then kind of stationary there. So although there's motion, what standing wave really means is that there's no clear propagation direction. So you can't say that whether this wave is moving to the right or the left, it's just kind of stuck in place, oscillating up and down. So that's where the word standing wave comes from. And that actually explains a lot to us how musical instruments work. So we will see that shortly. So, you might think, how come we just have this string on a guitar, for example, attached, that when we pluck it, we get this nice sound, which is all one tone or one frequency. What makes it that way? It's not that you had some kind of source like here, which was set to a specific frequency, yet we get one specific frequency out of it. The same with wind instruments. So it's this idea of standing waves, which will help us explain it. And then we will actually use standing waves to try to make the leap to quantum mechanics. So we will see how are these things at all related to quantum mechanics. So that's coming up. All right, so let's think about what's happening to this wave on a string when it reaches an end. So if this end is fixed, meaning that it's fixed in place, this rope is tied to that end, What does that mean? It means that that wave cannot have a displacement there. So when it's reflected, so this red one is representing the reflected wave, which is going back, it has to get inverted. Why does it have to get inverted? Because at this fixed end, it has to become destructively, it has to destructively interfere because there cannot be displacement there. So it gets inverted, and then this interference happens as the wave moves right and left. Now, we'll look at another type of standing wave where you actually, it's not fixed, but it's a free end. So just imagine you cut your rope, but you don't attach it, and you still move it up and down with some frequency generator, but then it has an end, it's not continuing forever. That also will create a reflection. But in this case, there could be amplitude displacement here, and in fact, that's where the displacement becomes maximum, when there's interference. So the reflected wave just stays the same orientation as the incoming wave, so the same side up, and then you get constructive interference there. All right. So again, to kind of summarize before we go into a more mathematical description of standing waves, move this. So when do they occur? Again, all you need is one source, but you need this counter-propagating wave. So waves that are moving right and left that interfere either destructively or constructively at some point. So you could see here at these, this point and this point, that's destructive interference, and the same at the ends because there's no amplitude there. Where over here, that interference is constructive. So points of destructive interference, we call those nodes, just to describe some features of the standing wave. And points of constructive interference, so right here and right here, we call antinodes. But one thing that makes these standing waves really special is that there are only very specific wavelengths that can give these standing waves. So let us see why. So before we get to that, just rules that you kind of, as you're generating standing wave patterns, that you should keep in mind that nodes and antinodes have to alternate, and that when an end is free, that gives you an antinode, so that's the one that has amplitude, and the fixed ends are nodes, no amplitude. Okay, so why is it that only specific wavelengths can fit? Well, if you can imagine, you have a string which is some length L, and if you know that the two ends have to be kind of the these nodes or your equilibrium displacement or zero displacement, then there's only certain ways or certain patterns that you can draw to make a wave. So if you start with the longest possible wavelength that you can draw, it would look like this. You could just start with these two nodes here, you know those are nodes, and just connect them directly. So what is that? Well, that's half a wavelength. It's half a cycle. So in this case, if we want to relate the wavelength to the length of the string, or the distance between the two boundaries, the wavelength is 2L. And this is what is known as the fundamental or the first harmonic. So if you're a musician, you might start seeing familiar vocabulary here. Okay, so but that's not the only way we can create a wave. We can imagine, okay, so again, what you need to have is these two nodes at the end. So they don't necessarily have to connect directly. You can fit one wavelength in between these 2 points. So you can first go to an antinode, then to a node, and back to an antinode and back to a node. The dashed line, by the way, just kind of represents a later period, a later time where this standing wave oscillates back to minimum displacement. So that's maximum displacement and minimum. So you can imagine this is oscillating up and down. So in this case, the wavelength is exactly L, this distance. But you can go on. This is, again, not the only two possibilities. You can imagine doing this, as you see here. So what do we have here? We have a wavelength and a half fitting in this L. So if we solve for wavelength, it's 2/3 of L. It's just this region of L, which is exactly 2/3, gives you one wavelength. So this is known as the fundamental or the first harmonic. This is known as the second harmonic, or sometimes as the first overtone. This is the third harmonic or the second overtone. And you can imagine building this infinitely, these different wavelengths, and you kind of see a pattern. So here you have 2L, and this is equivalent of 2L over 2, and this is 2L over 3. And if you kept going, the next one would be 2L over 4, then 2L over 5, and so on. So you can write the wavelength for any n, for any harmonic, this way, 2L over n, where n is any positive integer starting with 1, which gives you the fundamental harmonic. So having now all the possible wavelengths you can fit, we can figure out all the possible frequencies we can have, because we know the relationship between wavelength and frequency, and it's given here. We know that the speed of the wave is frequency times wavelength. So if we solve for frequency, and the subscript n means for a given harmonic, it's speed over wavelength, and then if we plug this in, this expression for wavelength in here, we get v times n over 2L. So what you see here, what this is telling us, both by looking either at wavelength or frequency, is we can no longer, like in a regular wave, have a continuous possibility for the frequency of our wave, but rather these frequencies are now discrete. So this n here is an integer, so again, it cannot be continuous and discrete. And another thing that's very different about standing waves, so so far all along, what have we been saying? We have been saying that frequency is something that's source dependent, and wavelength, it's something that depends on both source and medium, because that's a connection. This was source and V was medium, and then we got wavelength. Now here it's different, because what we're fixing here is the wavelengths. There's only specific wavelengths that are allowed, and it's now the medium, and the wavelength, which determines the frequency. So things are a bit reversed here. We can't just say, let's choose a frequency and that's going to give us a wavelength. We are fixing the wavelengths, and that's what's giving us the frequency. So how can we, what's the way that we can change the frequency is now by changing the speed. So if we're talking about a guitar, how do you change the speed? Well, remember, speed is something that depends on the medium. So when you're tuning the guitar, when you're turning one of those knobs, what are you doing? What you're doing is you're changing the tension in these strings, and changing the tension changes the physical property of your medium. So it changes the V. Again, lambda is not something that we can change directly, because lambda depends on the length of that string. So by tuning it, you're changing the V, thus you're getting the desired frequency that you have. So when you pluck your string, basically what are you doing is you're exciting all these different harmonics. Typically the fundamental harmonic is the dominant one. So that's the one that you're most likely to excite, especially if you kind of pluck the string right at the center. And that's why all the other ones that could be excited as well, but not with as big of an amplitude, they're known as overtones. So basically what this standing waves on a string with two ends fixed, what they describe is the behavior of string musical instruments. Now you can now imagine another type of standing wave where we have one fixed end here. So imagine take a rope, we tie it, and then one free end. So you're not tying into anything, you're just kind of letting it oscillate back and forth. Now in this case, we know that we must have a node here and we must have an antinode there. So the longest wavelength you have is actually a quarter fitting in a length of L. So here wavelength is 4 times L. The second one here is that when you start at a node, go to an antinode, then there's one more node, and then you go to an antinode here. So what you see here is, so if this is a quarter, 3/4 of a wavelength fitting in L. So L is 4/3, or lambda is 4/3 of L. And again, you could continue. The next one ends up being 4L/5, and so on. So here the pattern is a little bit different. So you have here 4L/1 for the first harmonic, 4L/3, then 4L/5. So if you were to take a guess, the next one would be 4L/7, and so on. So what you're seeing here is only odd harmonics. You only get these odd multiples. So that's why this is known as the fundamental again, but also could be called the first harmonic. This is the third, the fifth, but in musical languages, this is still known as like the first overtone, the second overtone, and so on. How do we write this mathematically? Well, it's 4L over an odd number. So we could represent this odd number as 2n minus 1, where the n's are still being counted the same way. So when n is 1, we get 1. When n is 2, 2 times 2 is 4 minus 1, we get 3, and so on. And again, we can solve for frequency here, and what we see is we get a slightly different expression for frequency. But as for the case of standing waves when two ends were fixed, again, what we're seeing is this discrete wavelengths that we can have, thus discrete frequencies. We can no longer have any frequency that you want that you would have on a continuous wave. So, of course, this is a bit of a bizarre situation. String instruments for sure don't behave like this, because all string instruments, whether you're talking about a guitar, viola, violin, they have the two ends fixed. So what could this describe? Well, many wind instruments actually behave that way. So when we're talking about wind instruments, what is really oscillating inside there, or what is causing our standing waves, is air. And air, when we talk about displacement of air, what we're really talking about is displacement of pressure. So, forget about standing waves in general. When we talked about sound waves so far, what made them waves, what was happening, it was really this pressure that was changing. So whenever we talked about maximum or amplitude or maximum displacement from equilibrium, what we meant is either maximum pressure or minimum pressure. So when we have a pipe of this nature where we have one closed end and one free end, that's again confining your wave to a particular constraint. The same way you did with a rope when you tied it to the two ends. Here, when the air hits this end, it can have, that's a pressure antinode, because these particles either get smushed together or spread out, so which is known as rarefied. So this acts like an antinode, where on the open side, that's a pressure node. Why is it a node? Because remember back from 7b, whenever your system is open to the atmosphere, the pressure has to match. So no matter what's happening here, the pressure is fixed at the open end, it's just at atmospheric pressure. So that's why it's node, or equivalent of, our destructive interference. So it's a little bit reversed, because before we said fixed end was a node. Now open end is a node. So just make sure you have those two ideas straight in your head. So an instrument like a clarinet here, where you're blowing in one side of it, that represents equivalent to this situation, a pipe with one fixed end, because where the mouth is, you're covering the airflow there, and that's where the pressure is able to vary. Where the open end here, that represents your atmospheric pressure, so your node. So this instrument would be described by this structure of standing waves, equivalent to one fixed end and one free end. But then we can have wind instruments that behave exactly the same as a string, which is tied to two ends, something like a flute, where you're blowing air from above, and both ends are open to the atmosphere. So both ends there represent a node, so those two ends are fixed. So a flute would be described by this type of standing wave structure. All right, so here's a couple of questions I want you to think about. So again, you're watching this video, you should pause and read through it and think about it, but let me read it for you now. So here, you press down with your finger in the middle of a guitar string. So you imagine your guitar string, you press on it in the beginning and such, and then you pluck only one side in such a way that only half of the string now vibrates, not the whole string, but half. How does the sound that is produced compare to the one that is produced from the original entire length of the string? So, you know, part of the things that musicians do is that they change strings, but then they also put their fingers on different part of the string. So, you know, what is the point of that? If all you had to work with is those 5 strings, or whichever many your string instrument has, then that means that you could only produce 5 different frequencies. So there's another way that you can produce different frequencies, and that's by changing the length. So I'm kind of already giving you some of the answers here. All right. So, and then let's assume that whether your string is the full length or the shorter one, half of it, you're exciting the fundamental harmonic. So what happens to the frequency of the sound produced when you cut, in a sense, or reduce the length of the string by half? So think about this. All right, so the answer is now you will have a higher frequency. So how do we know this? Well, if we go back to this expression for frequency for 2 fixed ends, what we see, it depends on the speed. We haven't changed the speed. The way we would change the speed is actually by going to a different string, because the difference between the 2 strings is, well, part of it is a mass density, but part of it is the tension in the string. So that's physical properties of the medium, thus the speed. Here we're working with the same string, but we put our finger in the middle. What did we change? We made L half. So what did we do to the frequency? We have doubled the frequency. Considering N is fixed, fundamental harmonic means N is 1. All right, now a slightly different scenario. So here we have a string with both ends fixed again, which is now being driven by a frequency generator. So now you don't have a choice, in a sense. It's kind of like in that image that I had in the beginning when I was introducing standing waves. There's a frequency generator that you can, which is oscillating and creating the standing waves, and you can imagine kind of turning the knob and fixing that oscillation to a specific frequency of 400 hertz. And it happens to make a standing wave in the second harmonic like this. Now, imagine you pinch the string in the middle right here, and you kind of pinch it in such a way, imagine that the generator is on the left, that only this part of the string is able to vibrate. Now, what's going to happen? So here we're fixing the frequency. What's going to happen to the vibration? So think about in what harmonic it's going to vibrate and what's happening to its wavelength. So let's take a look. So here in this example, because we can no longer change the wavelength, or we can no longer change the frequency. By pinching it here, what's happening is that now you're just allowing your standing wave to form in half this distance, but we have to have the same frequency, so we have to have the same wavelength. So here, the wavelength is such a way that half of it fits in this distance. So if we look at the picture here, it's exactly the same wavelength, except now on your constrained length of string, only half of it fits, where in this case, the whole thing fit. So the wavelength is the same, but we started with the second harmonic and we went to the first harmonic. So this is not what happens to guitars, because in guitars, we're not fixing the frequency. So by changing the length, you're actually changing, you're always, let's say, exciting in the fundamental harmonic. So by changing the length, you're gonna change the frequency. Here, for example, if you pinched it, so the only place you could have really pinched it and still get a standing wave is right here, because if you pinched it somewhere over here and your length is now, let's say, 1/3 of the original length, this 400 Hertz would not give you a standing wave. So because remember, not all frequencies can give you a standing waves, that only the ones that give you that specific wavelength that can fit in that length. So again, in this case, the only place that you could pinch it is right here to still get this standing wave pattern. It's just now in the first harmonic. All right, so now what we're gonna do is think about how this idea of standing waves can possibly lead us to thinking about quantum mechanics. So that's what we're gonna do next. All right, so I started this lecture by reminding you about the, Young's double slit experiment. So that was a laser, which was light, that was shown through these two slits that created diffraction patterns. But what turns out, and this was kind of observed in the 1920s, that particles can diffract as well. So we've kind of concluded that light is a wave, and we were happy with that and can diffract. But what explains this experiment? So in this experiment, there was, instead of a laser, there was an electron beam gun, which basically just shot out particles, electrons, and it even did them, the frequency was pretty low. So it's not that you had a bunch of electrons coming through at the same time, is that, let's say you shoot one, you wait, you shoot another one. And if you looked at the screen, so this was, let's say, only after, less than 10 of them were projected onto the screen, they do behave like particles. You have a dot here, kind of makes sense, except as you continue doing this experiment, what magically appears is this very similar diffraction-like pattern. So you get these bright spots here, as you see on this. So this is kind of more of a real image, but this is sort of a drawing of it. So you get this central bright spot, and then this very periodically periodic distance between the bright spots. So it's as if this particle, remember, they're just being sent one at a time. It's as if they're somehow interfering even with themselves to cause this type of interference pattern. And how is that possible with particles? Because we've kind of established only waves can display this type of interference pattern. So basically what this experiment told us, and this was one of the starting points of the development of quantum mechanics, is that we can't exactly think of particles as just having particle-like behavior. The same way, as we'll see later, we can't think of waves as just having wave-like behavior. And in fact, kind of the main postulate of quantum mechanics is all particles are like waves and all waves are like particles. So one of the first sort of mathematical descriptions of that is known as the de Broglie equation, which connects a physical characteristic of a particle, such as momentum. So particles have momentum, they have mass and speed, something that a wave cannot. We can't describe the mass of a wave, but that's connected, this momentum is connected to something that's clearly a wave property, wavelength. So it's a very simple equation, but it's very revolutionary because, again, it made this connection between something that's wave-like and something that's particle-like, and de Broglie won Nobel Prize just for this simple equation. Now, how do we think about, so waves, they had amplitudes and displacement. What does it mean for a particle to have amplitude? So, or for this particle wave? Well, this amplitude for a particle is now associated with the probability of finding that particle at a particular point in space and time. So if we go back to this experiment for a second, what this basically told us is that the particles, these electrons, had a very high probability of ending up where the bright spots are and a pretty low probability of ending up in the middle. So the first kind of very classic example that anyone studying quantum mechanics starts with is a particle which is, I think I missed one thing, one important point here. Okay, so these amplitudes have to do with probabilities, but also when your particle is bound in some kind of potential that keeps it fixed, so it's not basically allowed to exist anywhere in space, then these particle waves form this standing wave-like pattern. So the same way that we confined our string to two ends, and that gave us standing waves, if we confine our particle to some kind of potential, then these particle waves will exhibit these standing wave-like patterns. So the most classic example is thinking about a particle that we can confine in a one-dimensional box. Right, so this box has boundaries. What that means is, and especially if we think about these boundaries as infinite walls, so the particle cannot jump over them, that means that it's confined to the space, and then the type of standing wave patterns that that particle in a box creates is exactly like for a classical wave, which is confined to two fixed ends. So you see this was sort of like our fundamental harmonic, and this is kind of like our first harmonic, except now with what this is defined as is not amplitude, but what we know, what we call a wave function. And we use this capital psi to describe this. But what's really physical is the square of this wave function, because remember, amplitudes are now associated with probability, and probabilities cannot be negative. So what we do is we square this wave function. And whenever you have a peak like this, that represents the maximum probability of that particle being in that space. So if our particle is in this standing wave, then it has maximum probability being exactly in the middle, no probability at the edges because that's where the walls are. Now for this harmonic, we have two locations where it has maximum probability, but then right in the middle, there's zero probability. That's because that's your node. There's basically zero probability of that particle being in the middle of the box. So it's quite strange, but again, it has to do with this wave nature of particles. So like for our more classical string fixed to two ends, we have that same pattern of allowed wavelengths that our now particle wave can have, 2L over n, where n is any positive integer. And what we can do now is we can relate this to energy, or specifically kinetic energy of our particle, because our particle is just there inside this box, and the only type of energy it can have is kinetic. It can move around. And we know back from even 7-8 days that kinetic energy is 1/2 mv squared. We can also express this in equation in terms of momentum, because remember, momentum is m times v, So if we put another square here, then we divide by m, we get p squared over 2m. And then we can use this clever de Broglie's equation that connects momentum to wavelength, and then rearrange, so plug that in there, do some rearrangements, then plug in for wavelength these discrete values that are possible, and we get this expression for energy. So kind of dropped kinetic energy and just said, you know, the energy of this particle, this n represents these different integer values you can have. So you could see what's, you know, why is quantum mechanics called, what's the word quantum means? It has to do with the fact that things are quantized, or in this case, energy is what's quantized. So our particle, you know, classically we're used to, you know, our ball having any available kinetic energy. You know, you give it some speed, that speed can be continuous, you can have continuous value of kinetic energy. But what this equation is telling us is that's no longer true, that energy is discrete, and it goes up by these discrete values of this integer. In this case, for a particle confined in 1D box, it goes as n squared. But remember, your particle needs to be confined to have this discrete nature, exactly for this reason of these standing wave-like patterns for these particle waves that get created. So let's take a look at how these energy levels, oh, okay. Before we do that, I will want to talk about now an experiment. So we looked at this experiment with particles through a double slit, giving us diffraction, which sort of told us that particles have wave nature. What about light? You know, we saw that, okay, Young's double slit experiment proved to us that light is a wave. So is there an experiment that proved that light actually has particle-like behavior? And the answer is yes. It is known as the photoelectric effect. So let me just quickly describe what it is. So you imagine some metal, which, you know, has a bunch of electrons in it. You shine light on it, and that light, it's a, you know, originally we thought of it as a wave. It carries some energy, and then it can, you know, if there's enough energy, it knocks out these electrons. And then, you know, how much these electrons get knocked out can be measured by, let's say, current. So, you know, this experiment is much more complicated than this, but that's sort of the basic description. So what was the prediction? So when light was thought of as a wave, what could you predict? Well, increasing the intensity of light, or in other words, brightness. So we thought about intensity, that's something that has to do with energy. So if you increase the intensity of the brightness of light, that means that there's more energy coming in. So then the electrons that get knocked out should be more energetic. They should have higher kinetic energy as you increase intensity. Also, if light is a wave, what should frequency do? Well, frequency should increase the number of electrons getting knocked out. So the more frequent this sort of wave is, the more electrons get knocked out, so you should measure higher current. But in fact, when this experiment was conducted, the complete opposite was observed. So first, that light frequency is what increased the electron energy. So it was the frequency or the wavelength of the light which determined how much kinetic energy these electrons have. So completely opposite of the way we thought about waves. And also what the intensity increased is not the energy, but the current. So if you increase the intensity of this light, it would just knock out more and more electrons. If you increase the frequency, the electrons that were knocked out had higher and higher frequency. So how could this be explained? Well, if you think about intensity, if light instead was a particle, not a wave, then intensity or brightness would have to be with how many of these particles are bombarding this metal. So the more particles, that's the higher intensity, the more electrons you would get knocked out. And then frequency would be some physical characteristic of this sort of light particle that determined its energy. So the higher the frequency, the more energy that light particle had, thus the more energy it got transferred to the electron. So, you know, again, this photoelectric effect, what it really proved is that light has this particle-like behavior. And it was Albert Einstein, in fact, who sort of came up with the explanation of the photoelectric effect. And he called these light particles photons. So he's the one that came to the rescue, although Albert Einstein is perhaps more known for his theories of relativity, sort of going back to the discussion of gravitational waves. It's this experiment what gave him the Nobel Prize in 1921, or not the actual experiment, but sort of making conclusions and explaining this experiment in terms of the particle nature of waves. All right, so we kind of saw now that particles can exhibit wave-like properties, and now waves, light, can exhibit particle-like properties. So the photon, how do we describe it as a particle? It's this photoelectric effect that proved that light is a particle. And now this light now can only be absorbed. In other words, like when the light was shined on this metal, it was being absorbed, or emitted, as we'll see examples. What does it mean for something to emit light? So it's kind of, you know, depends which way energy is going in. Is it decreasing? Then we can get an emission of light, or it's an increasing, we get an absorption. And what is this? How is the energy described of this photon? Well, it's described by, I think I forgot to mention in the previous slide when I showed the de Broglie equation, but there's this H that keeps coming up, and this is known as it's just a constant. It's known as the Planck's constant, and it has this value here. So the energy of the photon is given by H times F, its frequency. So you could see now how that explains that the higher was the frequency of the light, the more energy those electrons had when they were ejected from the metal. And then F can be also written as c, which is the speed of light. That's how fast light travels, over wavelength, because we know that speed is just frequency times wavelength. So that's another common form for the energy of the photon. And there's a nice relationship of H times C, which is right here. It's 1240 electron volts times nanometers. Electron volts are a unit of measurement of energy. We'll see that shortly again. And nanometers is a length. It's a common measurement of wavelengths, especially in the range of visible light. So then if you use this, then you get your answer directly in nanometers. All right, so now let's think about how we think about photons and this discrete energy levels that we have talked about. So let's go back to our particle confined in our one-dimensional box. So remember, this was the energy that we came up with, where these energies were discrete and they were proportional to n squared. So we often depict these energy levels in diagrams like this, where we kind of draw a line for each energy level and then think about what's the difference between the very first energy level, that's when n is 1, and then the second one, and the third and the fourth. And you could see, because it's proportional as n squared, the energy levels get wider and wider apart. So that, you know, if this is proportional to 1, this is 4, this is 9, and this is 16. So they get farther and farther apart. And what we can think about is, how do you get a particle, which is in this energy level, to jump up, to increase its energy? So we know back from 7a, to increase energy, you have to get that energy from somewhere else. What can give us that energy is something like a photon. So if a photon comes in, it can, get absorbed by this particle in such a way that it jumps that energy level. But because these energy levels are discrete, there's only a very specific energy of this photon, which has to equal exactly to that energy difference. So the energy of the photon has to equal exactly the difference in the energy between those two energy levels for it to get absorbed. So even if that energy of the photon was a little bit more, so let's say if this was like 2 electron volts, if it was 2.1 electron volts, it wouldn't be absorbed because there would be no energy that that particle could go to. It only is allowed quantum mechanically to have these very specific energy levels. So we can actually calculate exactly what type of frequency this light must have in order to cause this transition in energy level. So the energy of the photon, remember, is h times f. And the transition we're curious about here is from 1 to 2. So energy 2 is our final state minus energy 1. Now these energies are these energies for our one-dimensional box, so we can get them from here. So all of this stuff is constants. And then the transition we're making is from N2, from N1 to N2, so our final is 2 squared, and the initial was 1 squared, so we get 4 minus 1, a factor of 3. Then we can solve for the frequency, divide by h, so we get this expression. So we can figure out exactly what is the frequency of this light required to make that transition. All right, so this particle confined in a 1D box, it's sort of a toy example of a simple way to start thinking about quantum mechanics and particles confined and potentials. Now, a more realistic quantum mechanical system is, first of all, not one-dimensional, but three-dimensional. And one example is a hydrogen atom. And specifically, what is being confined are electrons that are orbiting the nucleus of this hydrogen atom. Why are they confined? What is the potential that's confining them? It's the electrostatic potential. So the nucleus is positively charged, electron is negatively charged, they attract, so that potential confines the electrons, so the electrons can just fly off into space without being given some energy. So in this case, because our system is now, our electrons are allowed to be in orbit in three-dimensional space, we no longer have this toy one-dimensional standing waves like a string confined between two ends, but in fact we have three-dimensional standing waves. So instead of forming these sine functions with certain wavelengths, they form a much more complicated patterns, as you see here, and these might be very familiar from your chemistry class, that they're called orbitals, atomic orbitals. And what do these represent? These different lobes represent our antinodes. So these are locations where those electrons in a given orbital have maximum probability of existing, and kind of points in between those nodes. Remember, nodes and antinodes have to alternate. So the points in between those antinodes are nodes. So like right here at the center, this is where the electron has 0 probability of being. And some of these orbitals have much more complicated shapes. So these are associated with kind of particular frequencies, thus particular energies that those electrons can have. And what exactly is those energies? So for any hydrogen-like atom, so when there's one electron, the energy levels are described this way. So the Z is the number of protons or atomic number, which for hydrogen is 1. And now you see, unlike for a 1D box where the energy levels were proportional to n squared, in this case they're inversely proportional to n squared. And also there's a negative sign, so the lowest, the n equals to 1 energy level is the one that's the most negative. Remember, we have some freedom of deciding where our energy level is 0. In fact, here, how do we get 0? It's when n is sort of goes to infinity, so the very last energy level, because kind of thinking back to the Lennard-Jones potential, when our particle is confined in a potential, we give that a negative energy, and when it's free, that energy is 0. All right, so again, we have these units of electron volts. These are just convenient units on an atomic scale that we use, and it goes as n squared. So when you draw this, how energy increases and how the gaps between different energy levels change. In the case of a 1D boxer, we're getting wider and wider apart. Here, they're actually getting closer and closer together. Why? Because exactly of it's going inversely proportional to n over squared. So the biggest gap between energy levels is between 1 and 2. And then even between 2 and 3, that gap is smaller. But the same physics applies. In order for your electron to go to a higher energy level, it must absorb a photon exactly of that frequency or wavelength that's associated with that energy gap. So for example, if a photon comes in and its frequency is exactly the difference, or its energy, which is h times frequency, is exactly equal to the difference between those energy levels, then that electron is able to transition to a higher energy level. The same thing happens with emission. So what is emission? So if your electron is already sitting up there at a higher energy level, it's not typically a stable state, so it wants to drop down to a lower energy level. When it drops down, what happens? It loses energy. That energy, where does it go? It goes into the emission of a photon. So the electron has now lower energy, but now it has created sort of a photon that has exactly that energy, which is associated to that energy difference. So this is why we have something as known as absorption and emission spectrum for different elements. So let's take a look at what this means. How do these kind of discrete lines tell us about the quantum discrete nature of energy? Well, if you imagine if you shone light on some sample of hydrogen of all these different wavelengths, so here we just see like the visible light range, because looking back at this picture, only specific wavelengths can be absorbed. So any wavelength which would give us an energy, let's say somewhere in between, just wouldn't be absorbed because there's nowhere for that electron to go. So all of those that are not absorbed are being reflected back, so you see this light, but the ones that are absorbed sort of disappear because they go into making transitions for the electrons. So that's why you see these black lines, which are exactly associated with the wavelengths which get absorbed. And you see also this kind of pattern of this wavelength being very far apart and then them getting closer and closer together, and that has exactly to do with that 1 over n squared relationship. And emission is the opposite. So when your hydrogen is excited and all the electrons are in excited states, as they relax back to their lowest states, they will emit photons, but they will only do that, those emissions at those exact same wavelengths as absorption. So it doesn't matter whether you emit or absorb, it's the same energy level differences. So you get now light coming out that has to do with emission, and all the dark spots are wavelengths that cannot be emitted from this hydrogen atom. So let's look at this one very specific line, this red light that's being emitted when a transition happens from the n equals to 3 to n equals to 2 energy level. And that's, it says here, that's associated with 656 nanometer wavelength. So how can we prove that? Well, let's look at this equation. That's our equation for the energy levels. And the transition we're making is from 3 to 2. So the energy difference, this is a constant, the minus 13.6. We go from our final state is 2, so 1 over 2 squared, or 1 over 4. Our initial state is 3, so minus, because we're looking at the energy difference, minus 1 over 3 squared, or 1 over 9, and we get a negative number. Why is it? Because our energy is dropping, it's decreasing. We're starting at a higher level, we're going down to a lower level. So what frequency of photon emitted is that associated with? Well, we can set that energy difference, or what wavelength, that's what we're looking for. We can set that energy difference to the energy of the photon, which is 8c over lambda. And wavelength is something that's a positive quantity. It's being emitted, so that's associated with the fact that the energy is dropping. But when we're thinking about wavelength, we want to know positive quantity, so we just put absolute value here, 1.89 EVs. This HC up here, it's that constant I pointed to earlier, 1240, and we get exactly this 656 nanometers, which is the number you saw here. All right, so I'm almost done here. Let's just look at one question. So the energy, again, just to remind you here are the energy levels for a hydrogen-like atom, and we are talking about hydrogen, so Z is 1. So photon is absorbed, resulting in an electron, which is initially in the ground state. So the N is 1 is known as the ground state. And then that photon that gets absorbed allows this electron to escape the atom. What does that mean? So what are the possible energy of the photon? So think about what it could mean for the electron to escape the atom. All right. So the answer here is it has to be equal or bigger to 13.6 electron volts. So what does that mean? So how does it escape from the atom? Well, it starts at n equals to 1. What's the very highest state energy level it can have? Well, n is a number that can go to infinity. So if we take the limit as n goes to infinity, 1 over infinity, we get 0. So when the energy is 0, that means that you have escaped all the energy levels. And if you start at minus 13.6, go to 0, that's exactly 13.6 electron volts that is required to knock out this electron, in other words, have it escape from the hydrogen atom. Once you've given it that energy, or even if you've given it more energy, now it's free. Once the electron is free, it no longer has to have quantized energy. Now it's free, it's not confined to any kind of potential. It's not forming any kind of standing wave-like patterns which restrict the energies it can have. Now it can have any continuous kinetic energy. Thus, it could be 13.6 or 13.7 or 15, any energy beyond that, now it's a free atom. So that's why it has to be either equal to 13.6, that's exactly it getting to the last energy level, or anything more. All right, so this lecture had a lot of information and a lot of new cool stuff, standing waves and quantum mechanics. So you will spend some time, couple of DLs, sort of absorbing the stuff, but I hope you enjoyed it, and I will see you next time. Bye-bye.